What's up? In this video I'm covering this new exciting paper called Self-Attention Between Data Points Going Beyond Individual Input-Output Pairs in Deep Learning, which introduces this model called Non-Parametric Transformers. And now, non-parametric doesn't mean it doesn't have parameters. It's quite the opposite. So that it just means that it doesn't scale well with data. Basically, the more data you give it, the more parameters it's going to need. And in general, these non-parametric models either have this time-wise or space-wise / memory-wise dependency on the number of data points. So having said that, like the main idea this paper introduces is that it's a kind of attempt to generalize even transformers. So whereas transformers basically assume there is a fully connected graph between the input tokens, and so they kind of attend to everything. Here they additionally actually attend over different data points. So that means it's assuming an implicit fully connected graph over the data points. And I'll get into those details in a moment. And basically, even during the inference, they need the training data points, and they'll use those to better infer the class or the value if you're doing regression of the test data point. And we'll see all of those details. So that's like the main innovation that this paper brings. They get a really nice results on some tabular data sets, which is something that previous methods like XGBoost were dominating. And yeah, that's pretty exciting. So having said all of that, let me jump into the details of the paper. They say here, we challenge a common assumption underlying most supervised deep learning, that a model makes a prediction depending only on its parameters and the features of a single input. To this end, we introduce a general-purpose deep learning architecture that takes as input the entire dataset instead of processing one data point at a time. Our approach uses self-attention to reason about relationships between data points explicitly, which can be seen as realizing non-parametric models using parametric attention mechanism. And again, you can see here, so entire data set, they are learning from the entire data set, and they are doing inference, as we'll soon see on the pretty much because it doesn't scale well with data, they'll have some simplifying assumptions and approximations, so they'll be using some chunk of the training data to do inference on. As I said, the model is called non-parametric transformers, and so a quick note here, like just on like conventional non-parametric models. So they say here, conventional non-parametric models cannot learn in the sense familiar to deep learning practitioners. Interactions from the data limiting the flexibility these models have in adapting to the data at hand. And a good example would be a KNN, K nearest neighbors algorithm. So just a quick note how it works, and you'll then understand what non-parametric models mean. So let's say we have some classes here, like maybe we have two classes, one is like triangles, and then maybe we have something like circles, something like this. So assume this is your data set, and now assume I give you a query point and I ask you what's the class of this data point. And now if we assume that k equals 3, basically that means we'll find the 3 nearest neighbors, hence the k nearest neighbors algorithm. So that's going to be this, and then we'll output by majority voting. Let's take that simple variant of the algorithm without including the actual distances, and either way we're going to have triangle here. So as you can see, the more data you have here, so if we had a bunch of different circles and triangles, and if k goes to infinity, and also assuming data goes to infinity, that means that this algorithm doesn't scale well, because you'll have to search for like infinite number of nearest neighbors. And so yeah, contrast that to maybe a neural network where no matter the number of data points, the size of your data set, you'll have a pre-specified architecture whose parameters won't change and the inference time won't change, because you always have to pass a single data point or a batch, whatever, through the neural network. So that's the difference between parametric and non-parametric. And as we'll soon see, now we'll see how the model actually works. So I first want to explain you the architecture itself and the data layout. So you can see here, their data set is tabular. So they basically assume, they concentrate on this single target regression and classification. That means the following. That means they are placing the attributes along, so these are data points, as you can see, along this axis,
we have here attributes, but in this last column, they're going to assume they're having like targets, either classification targets, like what's the class for these. So for this data point here, we have attributes, and this is going to be some like class, okay? Or if we're doing regression, that's going to be some continuous value. So that's just how they structure it. And as you can see here, if we had a parametric model, maybe a transformer, this is how the inference would look like. Except for the transformer, you'd have edges going here as well and here as well, because we are attending, every token is attending to every token, i.e. every attribute is attending to every attribute. So finally, we output the target value, whatever that is, either class or a continuous value. And here in MPT, as you can see, they're also leveraging other data points, so maybe some training data points, and basically using all of that information, they can reason and figure out this value, and they show that this inductive bias is really useful, so having the ability to attend to other data points as well. So that's an interesting shift in perspective, because usually we're used to this setup, but yeah, that's cool. Okay, so let me start explaining how the thing works. And first things first, like the objective is the following. So MPTs, so non-parametric transformers, training objective is to reconstruct a corruptive version of the input data set. Similar to BERT, we apply stochastic masking to both features and targets and minimize a loss on MPT's prediction at entries masked out in the input. So basically, they'll have a binary mask telling them which parts are masked here, and those will be predicted. And a quick side note on, if you're not familiar with BERT, it's very simple. It's a famous transformer. And the way it works, the way they train BERT is the following. So you have input tokens. So this is some sentence like help, prince, mayuko. And by the way, this is from Jay Elmer's blog. I'll link it down in the description. And what they do when they train BERT is they masked out certain tokens. So this mayuko will be masked by like a special symbol called mask, whatever, with some probability. Or they'll just place some random value there, okay? And they do that for a number of tokens. And now the goal is to output Mayuko here. So output the correct class up here. So if they masked some token here, they'll have to output it here. So the final loss will just be, if you're doing classification, like they'll just do like basically cross entropy loss here, and they're gonna backprop that and train the model. So it's a self-supervised way of training, and I'm just ignoring for the time being for those of you who know how BERT works, I'm just ignoring this part of next sentence prediction and focusing on these, because that's the part that's really similar in MPTs. They're doing the same thing as BERT pretty much. Okay. So they also assume, as I said, that the targets are the final attribute of this table. So as I said, they're going to mask out these values, and they're going to try to predict those values. But they're also going to mask out some of the attributes as well. So you'll see that's a combination. Let's first focus on the high level picture. So this is, as I said, this is the input. So this is your tabular data set. You have n data points. You have d attributes. And some of the values are masked, so either attributes or the target values. So what they do is they first embed this data into this ND, and now we have dimension E here. And I'll get into a bit more details of how exactly the input and output embeddings work. But having done that, somehow, consider it a black box for now, what they do is the following. So they first flatten out this thing, and they apply a data point. So basically, the same thing as what Vaswani did in the original transformer. So we have self-attention from the original transformer applied here across data points first. So they basically attend, as you can see, these lines here. Every data point attends to every other data point. So we do Vaswani type self-attention. Then they reshape it, and then they do the same thing just across this time across attributes. And they repeat this n times, basically as a for loop. And then they didn't draw it here, but basically they have output linear projection layer, and that's the whole thing. The architecture is pretty simple. Now, if you're familiar with recently published MLP Mixer, and I'll link it somewhere here if you haven't watched my video, I've explained it there. But like you can see that if we treat patch like a data point, so MLP mixture like inputs an image, you split it into patches, and if we treat those patches as a data points, there is a similarity in the mixing part at least. So they also have, they also have the first part where they are attending over different channels, over different patches, so different data points, but the same channel. And here they have the part where they are attending the same patch but different channels. So that will correspond to different attributes here. So this corresponds to this part, and this part where they are attending over different data points corresponds to this part where they are attending over different patches. So I just thought that's a neat analogy, and other than that, they are not using attention. So the whole point of MLP mixture paper was to ditch the attention and just focus on the MLPs. So have even less inductive biases in this architecture. Okay, that was a small digression. Hopefully you found that connection useful. Now let me go and try and focus on explaining the actual architecture. So quick mention again, we focus on single target classification and regression, corresponding to a masking matrix M with ones at all entries of the table column X. That this is just means that the last column is masked. But online multi-target settings, imputation, self-supervision using input feature is also possible. So that's what I told you when I said, like, basically they can also mask some other parts of the input data, and that's really cool. So the cool part here is that, and I noted it here, basically it jointly learns imputation plus prediction. So in conventional approaches, what you usually have to do when you use those boosting methods, you have to have a two-stage approach. The first stage just imputes the values. And now, again, imputation just means that you're missing some values. If this is your tabular data, and let's assume you're missing some value, and I'll just denote that as a question mark, these algorithms usually have to maybe apply some heuristic, like maybe they'll have to attend over the same row and maybe find, I don't know, like mean or median and impute it right here. Or they can even train a dedicated machine learning model which will learn how to impute those values. Once the imputation is done, that stage is done, now they only can do prediction. Here, this model MPT does this jointly, and that's really cool because it can learn much better how to do imputation in this end-to-end deep learning scenario. Because basically it can also attend other data points and make much better, much more educated decisions here. So that's something I thought mentioning. And yeah, I'll get back to this equivariance thing, and I'll make some nice connections to graph neural networks. But like for the time being, let me just, again, I showed you the high level picture of how the architecture works. Now let me get into a bit more details. So again, I won't be explaining the actual self-attention mechanism. I made a video on that. You can check it out. It's basically Vaswani self-attention. So you've been seeing, if you're following like recent research, this is being used everywhere. So I'll skip that part, and I'll just focus on explaining the input-output embeddings. So let me just scroll down in the appendix. Okay. It's going to be somewhere here. By the way, the paper is really neat. They have they added really cool things like checklists and computational requirements, and also some societal implications. So I really love how the paper is written, and yeah, kudos to the authors. Okay, let's see how the thing works in the initial stage of the pipeline of the architecture. So basically, we have a data set. So this is the data set, tabular. So we have n data points, we have d attributes. One of them is also the target column. So implicitly that's the last column. And how it works is the following. So they say it here, we'll learn separate embedding weights for each attribute. And that makes sense because each attribute contains its own semantics. And we'll now see even in more details why that is. So let's say we have this column. So let's assume this column contains categorical variables. So we'll have a certain number of classes there. And the first step they do for a categorical variable is they just basically encode it into a one-hot encoding. So this is going to be size of C, where C is the number of classes. And basically, so let's say if we have a number, I don't know, 2, and assume we have, I don't know, maybe 4 classes, this is going to be embedded into a one-hot vector like this. So basically we have 4 slots here, and 1 goes here, 0s elsewhere. Okay, so they're gonna embed every single attribute in that column across different data points into that one hot embedding. Okay, so the next step they do is they append the mask here. So they'll append the mask down all the way down, right? And they do this for every single column. So now let's assume this one is maybe continuous variable. The first thing they do here is they standardize the column, so they just make it have mean of 0 and standard deviation of 1, or variance equal to 1. And basically now after they do that, they'll just have a single dimension here, so that's 1, not C, and they'll append the mask again. Okay, so that's going to be 2. And as you can see, and also some different column may have different number of classes here, so it may be C prime, whatever. And that means for that reason, we'll basically have to have different independent linear projection layers, not just because of the semantics, but also because of the pure shape mismatch. So you can think of it like both ways. So once we have that, we just have like linear projection layer, so which will just project all of these, so whatever the number of dimensions here is, into E dimensions. So this is going to be kind of projected into, like you can imagine having a fully connected layer here, blah blah. I don't know how to draw today, but basically you can imagine it like this is, you'll have E dimensions, and we'll end up with a n times D times E volume, the same thing you saw on that high level diagram. So that's the embedding part, almost. Let me just show you the formula. So this encode, this is the part that embeds the categorical variables into one hot embeddings. Then they append the mask. So again, the mask will just have dimensions n times D, and if you have 1 somewhere, and I forgot to mention that part, if you have 1 somewhere, that means that part is going to be masked out. So let's assume this part here has 1. So that means they do the following. Aside from appending 1 here at the last like slot here, they're going to mask out all of this with high probability. So all of these will get set to 0. And so that means that one hot vector will just be zeroed out. So this one hot vector will just be zeroed out. So we'll have just all zeros all the way here. So as in BERT, this is either going to be zeroed out, or they're gonna just set a random value in there, and that's how the thing works. So again, getting back to the formula, you can see after we do the one hot encoding for categorical variables or just normalization for continuous variables, we append the mask, we project this into this E dimensions, and then we just concatenate across all the different columns, i.e. attributes, and then they additionally have these learned embeddings for index and type. I'm not sure whether they did ablation on whether they actually need the both of these, whether it can be jointly learned like the type and index, but yeah, if anybody knows or the authors are watching the video, they can maybe explain it down in the comments. Having done that for a single attribute column, so this is for a single attribute column, so this was this part, maybe we're focusing only on this specific column, on this volume. Now they just concatenate all of those, as you can see, across the axis D, so this is the D axis, and that's it. That's it. You get the NDE volume. And similarly for the output embedding, I'll just briefly explain it. So here, they're not predicting the mask variable, so they'll just end up with, so EJ was the notation they used to denote this part, without the masking dimension that's added. So they're just going to, again, linearly project all of these, this E into E, let's call it subscript D, where this is basically depends on the column. So for this column, this ED is going to be equal to C. For this continuous variable column is going to be equal to 1, etc. So yeah, that's basically needed so that we can then do the apply the appropriate loss across that column. So it's fairly easy. They say here, so it's 1 for continuous attributes, it's the number of categories for a categorical attribute, And to obtain the final prediction matrix, we take the argmax over the categorical predictions. So that's how they do the prediction. So basically, whatever they spit out in the last layer, maybe like they'll have some probabilities, obviously. So if I extract this part here, and then just make it a bit nicer to see. So if I extract it here, it's going to be some distribution, and like dimensions here are going to be C, as I said. So it's going to be just some distribution of across the classes, and they're just going to do like normal like argmax and find the highest probability class, and that's their prediction. Okay, that was lots of details on the architecture. Let me get back to the paper and tell you some interesting stuff. So first things first, I want to finish with the loss. So as I said before, so they're applying stochastic feature masking, they're applying stochastic target masking, similar to BERT. And during the training, we compute the negative log likelihood loss at training targets, as well as the auxiliary loss from masked out features. So that's the part I mentioned. So assuming we have a classification problem, what I do is the following. So they'll output, again, this will be the output of their model of the MPT. And let's focus on a single attribute on a single slot here. Basically, as I said, this is going to be C, and they're simply going to take the ground truth position. So maybe this is the ground truth class. They're going to take the probability that they had there. So let me just kind of draw it three-dimensionally here. So they're just going to extract the probability there, and they're just going to do minus log P of I. So in order to minimize the loss, you want to have your, obviously, so that's like cross entropy, simple stuff. You want to have your probability going to 1. This is the output Pi, and this is the loss, okay? The y-axis. So they just sum that out across all of the masked out features. So assume we had 1 here for mask. Assume we had, maybe if we had 1 here, we're going to additionally extract the class for that one and do minus log Pi, and we're going to just do a sum over those and just do a backprop through the model. Hopefully that was clear. So long story short, they're just going to sum up across all of the masked either features or targets here, and they're going to do a sum and just do a backprop on that loss, okay? So interestingly, stochastic target masking means that many training targets are unmasked to the model at training time. So this is interesting. That means that this column, which contains the targets, will not be like completely masked. So some parts will have zeros here, and that means that the model can actually see the correct target value for that data point. This allows MPTs to learn to predict at each epoch the masked targets of certain training data points using the targets of other training data points in addition to all training data features, okay? So that's an interesting part, and we'll see how that helps them do relational reasoning later on. Here, just a short note, obviously this approach will have some problems with scaling because they are attending like a bunch of training data points during inference as well. And yeah, that's something that future research will need to tackle with. Okay, architecture explained. Now let me actually show you some exciting results and first give you some connections to graph neural networks that I promised here. So first things first, they said here, MPTs are equivariant to a permutation of the data points. In other words, if the set of input data points are shuffled, so if we have the tabular data you have and n rows, d columns, so we kind of shuffle these rows, MPTs produce the same predictions but shuffled in an analogous manner. So that's the equivariance part. So it should not depend on their ordering. That's the important part. So now let me just kind of give you some connections with CNNs and graph neural networks, and hopefully you'll find that useful. Okay, where are we? Let me just find the... Yep, here it is. So, they mentioned here that MPTs can be seen as a conceptual generalization of graph convolutional networks. And again, I've covered that in my previous video. You can check it out. I'll link it somewhere here. And the other graph neural networks like GET, again, I've covered that one as well. So that's graph attention network, and GIN, in which a set of dependencies, edges between data points is not known a priori, and instead is learned from data using self-attention. So this is the interesting part. And now let me show you what they mean by that. So MPTs learn an implicit graph structure. So whereas if you're familiar with graph neural networks, let me draw a graph here. Basically, you have some nodes in your graph, and for example, for get, you'll have explicit connections here. Okay, you'll have something like this. And then what graph attention network will do, it will just kind of assign certain attention coefficients to each of these edges, and it's going to aggregate all of these node features. So every node has a feature vector associated with it. It's going to kind of aggregate all of these via some like invariant like mapping, and they're going to get the final embedding for this vector. So this was maybe, so prior to this, this vector had like a embedding vector v, and now after this accumulation across the neighborhood, so we're somehow modifying these feature vectors, we are somehow combining them, and we get v prime. That's the updated representation. So now the difference here is between get and in general the graph neural networks is they have explicit graph structure. So compared to that, MPTs, the non-parametric transformers, now do the following. They do something similar that transformer did with with sentences. Basically, it assumes a fully connected graph. So it assumes that all of these are connected with each other. Okay, I think I've connected everything. Basically, and now it just learns which of these edges have what kind of strength. And so it's implicitly inferring the structure of the graph without being said like which edges exist and which edges does not exist. So it's a more of a soft assignment here compared to graph neural networks. So that's the first connection. Second thing I want to mention is that like graph attention network is invariant to the data point ordering. So it's not equivariant, it's invariant. That means no matter how you have these node feature vectors in your table, so basically let's say this is 1, this is 2, this is 3, you'll represent your graph as certain table, where again here you have data points and here you have number of attributes. So no matter if you shuffle these 1, 2, 3 like in whatever permutation, you'll still have the same v prime feature vector here because what graph attention network does is it just sums up these values and basically sum enables us to have this invariance property, right? Because sum doesn't care about the permutation of your input. So on the other hand, let me take a convolutional neural network just to explain the equivariance part. I think you'll find it useful. Basically, let's assume we have an image here, and in this image we have certain like an image of a square, okay? And now if we pass that to a CNN, and let's assume we're in the first layer of the convolutional neural network, and that the first kernel, the first filter learns to just figure out the vertical edges in your image. So what the image will look like is something like this. We'll have something like this, and we'll have like 2 vertical edges here, okay? So the equivariance means the following. If we now take this square and we translate it here, maybe here, now what will happen in the output is this response will just shift by the same amount here. So as you can see, it's equivariant. It's varying with input. It's not invariant to the position of the square. It's equivarying, if that's even a verb, with the input, okay? So the invariant part in ConvNet usually comes at the classification head part, because there you really don't care. You just care that you have a square in the image. If you're trying to classify it, you don't care where it is. So it's actually a desirable property to have invariance at the latest stages of these CNNs, but like first stages have equivariance. So that was just a short summary of what's equivariance, what's invariance, and so basically now that we know that, we can say 2 things. First things first is that MPTs are equivariant. Second thing is that they are implicitly learning the graph structure over the data set, and that's really cool. But unfortunately, it's kind of computationally expensive. And yeah, they say here we'll leave further exploration of the close connection between MPTs and graph neural networks to future work. I just briefly mentioned a couple of obvious properties. I guess some of the more knowledgeable people from the GraphML community could write down comments of what interesting other properties this thing has with graph neural networks. Okay, that was it. Now let me jump to experiments. they have some really nice experiments. Okay, the first experiment they do is they basically test this on a tabular data set, a collection of tabular data sets, 10 of them to be precise. And they say it here, MPTs perform competitively on established benchmarks. Tabular data is ubiquitous in real-world machine learning, but notoriously challenging for general-purpose deep neural networks, which consistently underperform boosting methods and are rarely used in practice. So again, short note, boosting methods, they're super simple. You basically just take a weak learner, which means it's some really weak model that can be a bit better than random guessing, and they combine these in a clever way, for example, majority vote or something, to get something called strong learner, which actually has some nice accuracy, let's say if we're doing classification. So now there was a bunch of different work that came after the original boosting method. So there is, first thing is this add a boost. So that's just adaptive boosting, where once you create the first week classifier, let's say, you basically use the data points it's performing poor on to feed those into the next week learner, which will learn to perform much better on the points where this first learner was having difficulties with. So that's the add a boost. Then we had gradient boosting, and then there is a bunch of variations on gradient boosting. So here you can see XG boost, which is just a performance implementation of that gradient boosting method. We have cat boost, also gradient boosting implementation. Light gradient boosting method, again, gradient boosting, and yeah, so you get the point. These boosting methods are pretty popular on tabular data. You'll see them all around Kaggle. And now let's see the results they got, and they're pretty spectacular. If you take a look at this binary classification tasks, so I think there was 4 of these. You can see MPT is the first in this table. It's better than cat boost and light GBM, XG boost altogether. It's also the first on this table where they're doing multi-class classification, and MPT is again the best method. It's got a bit less variance compared to XG boost. They're otherwise tied here. And finally, we have regression tasks where MPT was a bit worse. So you can see it's tied with XG boost. It has a little bit bigger variance, and cat boost is kind of really good for this task. But nonetheless, they mention it here. So in addition to its strong rank-wise performance, MPT achieves best performance on 4 out of 10 benchmark datasets, more than any other method. So they definitely proven that this neural network can be used for tabular data and give some nice results. By the way, if you're asking yourself, maybe it's not fair, like they're probably used much more computation to train the MPT. That's actually not true, because for just figuring out the best hyperparameters for those boosting methods, they actually wrote something somewhere in the paper that the computation necessary was pretty much on pair. So this is supporting our hypothesis that attention between data points is a useful architectural inductive bias for prediction. And aside from these tabular data sets, they also tested MPT on the image kind of benchmarks, like I think MNIST and Cypher10. And they said here, similar to previous work on transformers for computer vision, we would expect pre-training on millions of images to significantly boost MPT's performance. And if you watch my previous video, you now know that vision transformers and MLP mixers don't need pre-training at all if you use this thing called sharpness-aware minimization objective. And again, I'll link the video somewhere here. You can check it out. Basically, if you somehow find a way to smoothen out the lost landscape, you'll notice that you don't need extensive pre-training anymore, and you can achieve results that outperform resonant baselines. And that's it in a nutshell. So I guess the authors of the paper either didn't have the time to rewrite this, or they still haven't read that paper, which recently came out a couple of days ago. Okay. That's the first part. Now let's see some cool things. This diagram here, let me just introduce it. Basically, they make this semi-synthetic problem, and they say here, for each batch, we input the original data with masked target values, as well as a copy of the original data where all target values have been revealed, i.e. no masking is applied. At test time, we input novel semi-synthetic test data to ensure that the MPT has learned the correct relational mechanism as opposed to just memorizing the target values. Okay, so they have a nice chart here where you can see what's the input. So this is the input. We have some data points, and we have the target values that are hidden, denoted by these question marks, and we have the actual correct values here. So if MPT is smart, even though we're gonna just backprop on these masked values, it's going to learn how to find this similar vector. So this is basically the same vector, and then just copy this value here. Instead of learning to somehow map and use the attributes, it's going to learn the relational mechanism. And why do we want that? Well, because it's going to generalize much better if it learns how to just attend to the same vector and just copy the value. That's the whole point of relational reasoning. So as you can see here, they draw some attention maps. So this green data point, so that's this one, the first one, it attends to this one. So that's this data point here. So that means it learned completely, and you can see attention here is 1, all around we have zeros if you take a look at this heat map. So that means the whole attention of this data point, of the first data point, is on this one. And that's exactly what we wanted. And you can see the pattern going for all of these data points here. And here, this part you can ignore. They didn't enforce this. They did write something about this in the appendix, why these data points are attending to themselves. So that's something maybe interesting taking a look into. But yeah, basically you can see the results are really cool. Pearson correlation is 99.9. That means basically a fancy way of saying that it basically learns how to copy over these values. Or that's a hypothesis for now, but like it's basically outputting perfect values as if it was copying them, and we'll soon see that it's actually copying them. So for this second row, let me just go back down here. Okay, so additionally we perform an interventional experiment to investigate the extent to which MPTs have actually learned the causal mechanism underlying the lookup task. And if you see these two keywords, and if you're familiar with Judea Pearl's work, you'll notice that this is basically rank 2 experiment. So we have this thing called letter of causation. The first letter is just observing data. The second letter would be acting in the environment, or doing these interventional kinds of experiments where you're setting something to a certain value and then observing. And finally we have a contrafactual level where we are imagining like different worlds, and that sounds super abstract for this context, but yeah, just I wanted to just associate this sentence here with Judea Pearl's work. So if you want to know more about it, you can check some of my previous LinkedIn posts, or you can read the Book of Why from Judea Pearl as a nice introduction to his work. So the model is now confronted with target values associated with features that are highly unlikely under the training data. And let's see why that is. So basically what they do, as you can see, so it's the same experiment as the above, but this time they take this target value and instead of basically keeping it the way it was in the original data set, they tweak it. They take that, maybe there was 1.3, and they're going to kind of mess it up and put 7.5 here. And that combination, 7.5, with similar attributes have never been seen in the training data set. So now if the model learned how to just kind of use the attributes and figure out the target value, it's going to fail here. And on the other hand, if it learned how to do what I previously mentioned, and that's just to attend to the vector and copy that value, it's going to have nice performance. And as we can see here, the Pearson correlation is again great. That means it learned how to, no matter these interventions, it learned how to predict the exact value from these slots, and that means it learned the correct relational mechanism. That's the point of these experiments. And so we now confidently conclude that the MPTs robustly learn the causal data generating mechanism underlying the semi-synthetic dataset. This requires MPTs to learn a non-trivial sequence of computational steps. They must learn to match rows based on similarity of relevant features, to look up the target value of the duplicated data point, and to copy that value into the target of the masked data point. So that's what I already explained, and yeah, hopefully now it makes more sense. Okay, Next experiment they did was to corrupt the data points and see whether it's failing because it learned how to actually rely on those other data points. So what I do, they said here, so this completely corrupts information from all data points except the one for which we evaluate. Hence, a model that relies meaningfully on attention between data points will show deteriorating performance. So let me just explain you what they actually did, and they did the following thing. So we have a data set here, and let's say we have a bunch of data points, and let's say we want to predict this value here. Okay, so this is the data point for which we want to predict the class. What they do is they just shuffle all of these attributes of all of the others, so all of these other data points are going to get shuffled, and that means this feature vector can't be matched now with other feature vectors in the you can't use the mechanism we just described it's using, and that's just figuring out matching the vector, finding maybe, I don't know, maybe it learned to do cosine similarity. Now it can't do that because we shuffle the attributes, and what they show is that performance deteriorates, which is a further proof that it learned the correct relational mechanism. It appears that when MPTs do not find it advantageous to rely on attention between data points during training, they can learn to completely ignore the other inputs, essentially collapsing into a standard parametric model. This supports our earlier claims that MPTs can learn end-to-end from data, the extent to which they rely on other data points for prediction. So that's a fancy way of saying that basically sometimes, if we have a data set again, so sometimes it's actually just relying on this particular row, on a single data point to predict this value here, because for that task you figure out it doesn't actually need to use other data points. And for those data sets, the performance they show does not deteriorate, which is again a further informal proof that basically it learned the correct mechanism. Here they just have a table, bunch of different data sets. You can see regressions here. So yeah, on certain data sets, as I just mentioned, it's not deteriorating that much because it doesn't rely on other data points that much. Okay. Having said that, let me see if we have something else interesting. And yeah, this is the last part that's super interesting. And they now try to figure out how the model finds those similar vectors. So, and what they do is we sort the input data with respect to their feature space. It's actually input space, as I saw in the appendix, but maybe the authors can correct me here. Distance such that the similar data points are now close to each other. And so let me explain what that means. Basically, that means you have the original tabular data set, you have your data points. What they do is they find, maybe using L2 metric, they find the closest vectors here, and they're just going to sort them. So now we have a vector here and a vector here, and these two have really small L2 distance. And now we have another vector here, and these two have really small L2 distance, which that means that basically these two also have maybe a bit bigger L2 distance, okay? So you get the point. Basically, we're slowly stacking vectors which are further away, looking at the L2 distance. And when we do that and we apply MPT, and when we look at a certain attention patterns from a certain head, we get this pattern. And this means that it's basically attending to the vectors which are basically close in the input space, which means it's attending to similar vectors according to this L2 distance. And if you don't know how to parse this diagram, let me help you. Basically, if this is row I, this row is going to attend, and assume we have a sorted table. So this table is sorted according to L2. So let's say this is I, this is vector I, and it's somewhere in the middle of the table, and that vector is going to attend to its proximity. So it's going to attend to these vectors really strongly, and then it's going to drop off, and then it's going to have really weak attendance to maybe this vector here. So it's going to attend to these vectors really strongly, and the strength will kind of fade away going downwards or upwards here. And that's exactly what you see in this attention map. Basically, if this is vector I, and this is just n number of data points, this is just n number of data points, this means that this vector, as you can see, attends to itself really strongly and to its neighborhood, but then it deteriorates because you can see the dark blue means the attention coefficients are really weak there. Okay, that's the whole point. And yeah, further they had some additional experiment where they're doing similar thing, but the conclusion was the same. Basically, MPT learns how to attend to those vectors which are really close in the input space, looking at the L2 distance. Okay, that's pretty much it. They mentioned some problems like these scaling limitations, which I've already flagged, and that's pretty much it. So we saw that MPTs learn how to do relational reasoning, and because they learn the correct mechanism on that simple semi-synthetic task, it can generalize much better than if they actually learn how to deduce the value just looking at the attributes, and instead they learn how to just copy paste the values from the corresponding rows. And yeah, hopefully this was useful. If you found this video useful, share it out and subscribe, and until next time, bye bye.